good theorem for this class. Do I have to? Just moved on. I don't know. I could somehow squeeze it in somewhere. There are moduli spaces. Yeah. It's close enough. They're not. I think the way things are going, another 3 years, the S will turn into Shenji somehow. I don't know. Stupid things and they're being recorded. Yes. I don't know if they're recording or not. I mean, before we start, we can do something. We're all here. How's the volume? Is that good? Can you hear me? I guess not. Nobody's responding, so I think nobody can hear me. Oh, you can hear me.
I can hear you.
First 2 rows. So.
Welcome to the second day of the workshop on SY linear symmetry and related topics. It is my great honor to introduce Professor Eric Zaslow at Northwestern University. He's the dean of SY. He'll tell us about Lagrangian feelings. What do sheaths say?
Yeah, the title is silly. It's a reference to some parody music video. What does the sheaf say? The fox doesn't seem to say much, but hopefully the sheaf will say something. Thank you, Melissa, and the organizers for the invitation. It's a pleasure to be here. Having said that, I now must apologize because I have no new theorems really to present, so I will be talking about some older theorems. the talk will involve joint works with the following people: Letty Eng, Dan Rutherford, Stephen Sivek, Vivek Shenda, and another one with Vivek Shenda, David Truman, and Harold Williams, and work in progress with David Truman. Okay, so those are the list of collaborators. Okay, so now let me begin. So pathological field theory says the following. To cobordisms, we associate maps. We assign vector spaces to codimension 1 slices. Let's call it plus. Let's call that minus. And the cobordism gives us a map. H minus has two components, so we have a vector space or Hilbert space assigned to each one of them. So in symplectic field theory, there's a little more structure on the codimension 1 slices. So we have a contact manifold, and let's say we have a cobordism of a Lagrangian submanifold in the contact manifold. And this will be some symplectic manifold. And the structure we can assign to a Lagrangian submanifold in a contact manifold is more rich than just a Hilbert space. There's a whole algebra, a differential graded algebra. So maybe I can call this lambda plus, lambda minus. And so differential graded algebra constructed with generators, the Rabe chords on this Lagrangian, and constructed by counts of holomorphic disks. And to this cobordism, we want to associate, say this is a Lagrangian cobordism. We want to associate a morphism of these. Okay, so that's a program. And in the special case, where you have a Lagrangian submanifold of the contact manifold, and inside a symplectic manifold, you have some Lagrangian filling. That's just a cobordism with the empty set. Then you get a map from the DGA of the Lagrangian to the DGA with no generators except the ground ring, which, for example, could be C. There are other coefficient rings that you can choose as well. And the 0 here indicates that there's no differential. So the 0 differential. And such a thing is called an augmentation, a morphism to the ground ring. Geometrically, if this is not a commutative algebra. If this were a commutative algebra, it might describe some variety, and such a morphism is the same as having a point in that variety. Okay. So let's now suppose that our contact manifold is the cosphere bundle, which I don't know, I write like this because I think of it as the cotangent bundle at infinity rather than at unit distance, but same thing. So let's suppose that that's our contact manifold, and our Lagrangian filling lives inside the cotangent bundle. So that's the symplectic manifold that has this as its contact boundary. Then such a, if, let's say it's an exact Lagrangian, and a brane structure exists on it, then we can think of it as an object in the Fukaya category of the cotangent bundle. And my Fukaya categories here going to be infinitesimal rather than wrapped Fukaya categories. And actually a little bit more than that, I can look at a subcategory of such a Fukaya category involving only Lagrangians that asymptote to this Lagrangian at infinity in the cotangent bundle. And I'm going to indicate that by putting this Lagrangian. Then this category has an equivalence, and the equivalence is due to David Nadler, and the equivalence in this context is also the equivalence when you look at these subcategories is due to Shin Jin, and also mentioned by David Nadler, and this relationship was also discussed in work with David Nadler and myself. So this is a category of constructible sheaves. These are not coherent sheaves. They're even easier. These are not sheaves of O modules. These are sheaves of C modules. So there's something combinatorial and topological. Locally, and you can think locally constant on strata of some stratification. So locally constant sheaves. And that way of thinking will get you far enough for our purposes. Okay. Any questions? So this is the context. We have a Lagrangian filling of a Lagrangian at infinity in the cotangent bundle, and that's producing an object in the Fukaya category, which we have a relationship to constructible sheaves. Maybe it's worth saying a little bit about this relationship. The prototypical constructible sheaf might be a constant sheaf on some open set. So let's say we have some open set in our manifold. That might not be big enough or high enough. Okay. And I can consider this is the constant sheaf on that open set, and there are two types of push forwards. If I just take the standard push forward, then the corresponding Lagrangian would be the following. It would be some vector field here, or the graph of the differential on some function that just goes out like that. So that at the edges, some infinite and outward vector field. Infinite because at the edges it meets infinity in the cotangent. And this one would the lambda here would be the conormal of the boundary of this open set. Okay, so that's an example of how this functor is constructed. In case this seems too obscure, just an open set you have the differential some function. Okay, so let me look at an important case of this setup, where you have the contact manifold is the standard contact manifold, the first jet bundle of a manifold, which I'll remind you is just the cotangent bundle. That's the differentials of functions. And then the first jet includes the values of functions as well. And the standard, okay. I can actually think of this as the infinite cotangent bundle of M cross R as two made dimensions here. Sorry, the dimensions line up, but there's too much here. So I put a minus sign, and these are the negative directions or negative codirections in the R coordinate. So let me just say what I mean by this. The one form, the exact one form on M cross R, we could write as follows. So let's say Xi is a coordinate for the covector of the Z coordinate on R, and we set that equal to -1. So negative codirections. That means C is negative, but at infinity, we can equate that space by stereographic projection. So here's of the infinite sphere with the C equals -1. And then our one form would be minus the contact form on T star M, which maybe we write y dx. And then when you say set this equal to -1, it's dz minus y dx, and that's the standard contact form of this. So I'll exploit that contact homomorphism. And this is an open subset of the infinite, the cosphere bundle M cross R. So that was just a way of saying that the contact manifolds that most people know and love sit nicely inside a cosphere bundle at infinity, and then therefore can be addressed with this equivalence, and we can construct a category out of a Lagrangian in a contact.
Why is it minus y dz?
I'd take my contact form here to be dz minus, oh, that's a typo, y dx. Sorry. Thank you. Summed over indices. Thanks. Other questions? That's great. Somebody's listening, and you can hear me. So two good things. Okay, so we can. That means that if I have a Lagrangian inside some jet bundle, I can consider this category here. Because I think of it as living inside my cosphere bundle. And then this, as we've mentioned, is addressed by a category of sheaves. And there should also be, based on this reasoning, some, these objects seem to correspond to augmentations, and so augmentations should also form a category. I'll remark on that in a moment. And if we have an exact Lagrangian filling, we get objects here. We have some corresponding sheaf over here. All right, about that. And we have some augmentation over here. And so, well, we have an equivalence of these two categories, and it asks the question, is there a category of augmentations which is equivalent to this category of sheaves? So that is a theorem. Well, I have to be a little bit, before I write that down as a theorem, I have to maybe, let's see one more thing. We could have considered augmentations to different places. We considered augmentations to a rank 1 ring here. And so if I'm going to actually try to make an equivalence of categories, I have to impose some analogous rank 1 type of condition on this side. And so we do that. So there's a functor. Which goes from this category of sheaves to local systems on lambda. I think it's probably best to explain that functor in a little bit, but this is the sheaf analog on the Lagrangian. I'll remind you that objects here are really Lagrangians together with local systems. So this, if you have this exact Lagrangian filling, it spawns a family of objects, and I'll mention that in a moment, because you can choose different local systems on that Lagrangian, different flat vector bundles. So it will also spawn a bunch of objects here. But when you have a local system on a Lagrangian whose boundary is this Lagrangian, you can map it, restrict it to the boundary, which is a local system on the Lagrangian. Okay, and we can make a sheaf theoretic analog of that construction over here. Then we can define the rank 1 sheaves, or the microlocal rank 1 sheaves, to be those that are rank 1 local systems. Okay, so now what we seem to have done is cut off or identified the piece of this category which should really correspond to augmentations. And then that's the theorem. These people. So in the case where you have a Lagrangian knot, so we take M to be the real line, and lambda is a Lagrangian knot or link in the first jet of the real line, which is just the standard R3 with its standard contact structure. So what you want to use for studying Lagrangian knots. Then we have this equivalence of categories. In this case, M cross R is just R2. And we have to put in maybe some compactness, compact support condition as well. And the reason I want to mention this is that the proof of this is that both categories are local. So sheaves are always local, the sheaf categories, but through the work of Stephen Sivek, he showed that augmentations are also local, and they can be built by augmentations of pieces of the front projection of your Lagrangian knot. So that's how the proof goes. Question? So this might all just look like symbols, unless I tell you a little bit more about how to use the sheaf category, and that'll be helpful to us.
So the right-hand side is always local. And
The right-hand side is always local.
And the left-hand side is.
The left-hand side is local through the work of Stephen Sivek.
In this dimension, or in that?
And this is just in this dimension. Building this equivalence in higher dimensions is, I think, work in progress of some subset of these people and other people, I think. Okay. Let me also reiterate the remark that if you have an object, if you have a geometric object, it spawns a bunch of objects. So I'll just say that. In fact, this Lagrangian L spawns a family of objects. How many rank 1 local systems can I put on it? I can, if I allow C-star local systems, I can choose a monodromy for each holonomy loop. What's the word? Homology loop. And so I have this many choices of monodromies. I get that many objects. And this is a chart in a moduli space, in some moduli space of objects. Okay, so whatever this moduli space is, it has charts which look like tori. Maybe there's your connection to this, to the idea of looking at moduli of objects and finding tori in the moduli space of objects. Okay, so now let me show you how this works a little bit in practice. Let me tell you, I don't need the augmentation category anymore for this talk, so let me tell you a little bit more about the sheaf category. You take your, look at the front projection. Of lambda. So in the case where lambda is one-dimensional, its front projection lies in 2 dimensions, so I'll remind you that this is the front projection. Okay, so you project down to the xz plane if you have a knot in R3. And in general, if I take the map, yeah, that's enough. So the front projection has different types of singularities. It's not even necessarily an immersed curve. It could have cusps, could have crossings. And generically, these are the only things that you might encounter for one-dimensional Lagrangians. And for example, if you looked at the positive trefoil, I think it's the positive one, or anyway, a closure of the 2-3 braid. Actually, your projection could look like any number of things because you could move the knot around through Lagrangian isotopy. And so, just like in ordinary knot theory, there are Reidemeister type moves that relate different projections of isotopic knots. And there are Lagrangian versions of those Reidemeister moves. So, that brings up a point that I forgot to say, an important point, that this category that we construct is invariant under Lagrangian isotopy. So that's work of Guillermo, Kashiwara, and Shapira. I mean, you wouldn't go through the work of constructing this category if you didn't think it was some kind of invariant of the knot. So invariant under Lagrangian isotopy. Okay, so now having said that, let me explain to you how this works. So this is living in 2 dimensions. If I want to recover the 3rd dimension, I have to remember where the projection came from, solve the equation that says that this is isotopic, so the y coordinate is dz dx, so you can figure out what y is. But since I'm thinking about these Lagrangians as living inside the unit cosphere bundle, I can just draw little unit tangent vectors as hair along these curves. And then, having drawn that, the category is easy to describe. Let me remind us that these are just local pictures of like what might happen in pieces of the front projection of a Lagrangian knot. So how do we describe this sheaf category? Well, the sheaf is locally constant on regions, so it suffices to give the stalk of the sheaf down here and the stalk of the sheaf up here, and some restriction maps that tell how they relate to the stalk of the sheaf right here. As it turns out, because of this condition, one of those restrictions maps is an isomorphism, or a quasi-isomorphism if you have if your stock is a complex and not a pure sheaf. So I'm going to forget that and just remember the non-trivial restriction map, which gives you a morphism of stocks from below to above, and that morphism, that map goes against the grain. And same is true here. So you have morphism this way, and these have to compose to identity. Same is true here. And there are some further relations, and all the relations come from this condition. If I call these stocks A, B, C, D, the crossing condition, which is the most important one for us here, says that if you look at the total space, first of all, these arrows commute, and second of all, if you look at this complex, the total space of that diagram, total complex of that commutative diagram, this has no cohomology, it's acyclic. Maybe this is the time to tell you how to do this. So here's a sheaf. It's supposed to represent some Lagrangian in some Fukaya category, a Lagrangian that bounds this knot at infinity. How do I construct some local system on the Lagrangian itself? Well, here this tells me how to do it. Take the cone over this map and say that that's what the local system is over here. That would define a local system. And then you could take the cone over this map, and that should be the local system over there. But if it's a local system, there should be an equivalence between these two cones. And this statement articulates precisely that that's a well-defined map.
So these sheaths, these A, B, C, D are sheaths or the stocker?
Those are the stalks of sheaths. So to give the data of a sheaf, you have to give the data of all the stalks and all these maps.
And so what are the morphisms between A to B plus C?
That's the data of the sheaf, is morphisms. So the data of a sheaf is restriction maps between stalks on different open sets. Right. So I've hidden a little bit. There's really three. Okay. Let's practice, and I'm going to only be interested in these sheaves that have the cones over these maps are one-dimensional. So let's practice with this diagram here. This condition that I've hidden there says that I want the sheaf to be 0 far away. And then there's going to be a map from 0 to the stalk in this region. And I want that cone of this map, which is just whatever this stalk is, to be one-dimensional. So that means that this is one-dimensional. And then I want the cone of this map to be one-dimensional. That means that this is an inclusion into this, and this is two-dimensional. For Maslow potential reasons, you take a shifted cone here. So this actually becomes a surge action. And then that's it. So that's the data of a sheaf here, is these 5 maps. And I can think of them as 5 lines inside C2. The last line being the kernel of this map. And this condition here, so in the case of 0, C, C, C2, this condition says that these 2 lines are transverse to each other. So if I call Li the image of this map, Li is not equal to Li plus 1 for these 5 lines arranged cyclically. So 3 of those conditions come from here, and the other 2 conditions come from the conditions at the cusp.
Why the maps are that direction?
That comes from analyzing what singular support means. One of the maps is an isomorphism, the other one need not be. Okay. So we have this. We've found the moduli space of objects here, and maybe all sheaf objects are fill-ins. Maybe they're not. Let me just mark that we would find the same moduli space for this map. I mean, for this Lagrangian in R2. If I put the hair going like this, let's say I'm going to decide that I can think of that as an oriented curve and just take the left directions for the hair. Now go through the same procedure, put in 0 far away. You'd have C and C2, and you'd have 5 lines in there. And you have a crossing condition at each crossing. And that crossing condition says that those lines are transverse in C2. Or if we think of, we don't frame this, we would quotient by PGL2 and think of these as 5 disjoint, 5 points in P1 with some condition on neighboring points.
So this is a Lagrangian projection?
This is a projection of no, this is the front projection. So I have a Lagrangian inside T infinity of R2, and this is the projection onto R2. I think that's the front projection. This is not a symplectic space. I mean, it happens to be, but generally speaking, if that's X, that would be X. Okay, so this space has a name, 5 points in P1, each distinct from its neighbor. And it's a well-known cluster variety. And you'll recall that if we had a filling, we got an automatic chart in this moduli space. It generated a whole bunch of objects, and those objects create a chart. And one might hope that that's a cluster chart, and that's the punchline to another joke. Maybe not a very funny one. So what we want to do is take this and find a way to construct a filling, and we have a way. So let me first try to draw this picture again. Okay. Now take this part of the picture and slide it down. Slide this pink down. You could remember which way the hair goes if you want. When you slide it down, you change the projection, but it's a Lagrangian isotopy upstairs. You don't introduce any crossings or anything like that. So let me try to draw what happens when I do it. This is the hard part. Okay. I haven't touched it yet. Now, take this and go like this. Slide it down all the way. This is a legal move. And when you do that, what happens? Let me, instead of drawing the hair, I'll just draw the orientation. Uh-oh. So it goes like this. So I haven't touched that. Okay, so that tells me what to do. Sorry for those trying to follow along. I'm speeding up a bit. It's going to get worse when I show pictures. Okay, the point is that there are regions here where these arrows are counterclockwise, and then there are other regions where the arrows are purely clockwise. And that corresponds to inward hair at these regions, the counterclockwise, and outward hair at the clockwise regions. If I just blow this up a little bit, here is very much like what we saw before. This looks a lot, except for the crossing, like an open set. And I can imagine building a Lagrangian filling by just choosing an outward vector field here. And choosing an inward vector field here. And I have to make sure that whatever I do makes sense over the crossing. But anyway, if you can create such a picture where you have these counterclockwise and clockwise regions, this is not the case for this picture here, by the way. You see that there's all these mixed regions. If you can do it, you can construct an exact Lagrangian filling from these such alternating alternating strand diagrams. And so the relation to clusters and bipartite graphs comes as follows. This picture are the zigzag paths of some bipartite graph. Put one color for the counterclockwise regions and another color for the clockwise regions. Clockwise. Connect them. Oops. Okay. So there is a bipartite graph there, and this picture is associated to a bipartite graph. And yeah. So each time you move this along, you get a filling, which gives you a chart in the space of objects. Actually, it's a little bit off. It gives you a chart in the space of objects of this category, not this one, but these categories are equivalent through the work of Guillermo, Kashiwar, and Shapiro. So you can translate this family of objects to a family of objects here. But you can see there's 5 ways to do this. And each chart, if you just look at what the Betti number of the corresponding Lagrangian is, it's 2. So 5 torus charts in 5 because I could have pushed 5 of these strands. So it's also known that this cluster variety has 5 charts, covered by 5 charts. So now we want to show that that these different charts are related by cluster transformations.
How do you know they're different?
Yeah, good question. So how do I know they're different? So I need to coordinatize them in some way and compare on some overlap of the charts. Okay. So we can do that explicitly. Other question? Let me do that now. Yeah.
So the 5 charts are like, you take the slide, each one of those corners of the star, the way you did.
Yes, I made a choice here in how I do it. In fact, 5 clusters. So I won't review what a cluster variety is here, but let me just draw the basic move where you can make the comparison of charts. So the basic move, it's called the 2-2 move in the language of bipartite graphs, if you've met cluster varieties in that language. Here we're describing cluster varieties as the space of objects of some category. So let me put some arrows. I'm confused. should be clear that this configuration can be arrived at from this picture by just doing this Lagrangian isotopy where you push this one to the right and this one to the left, and they don't cross each other because these arrows are pointing in different directions. The crossing condition identifies this. You see there's, let's see, we put 0 out here, C squared. There's 4 lines in C2, and the crossing condition identifies this as this big positroid stratum inside the Grassmannian of 2 planes in C4, which is a well-known cluster variety, but that's not our concern right now. What we want to do is take the filling, which gives us a chart of objects for this configuration, map it to this moduli space, and compare with this chart from this configuration, map that in, and compare directly what the coordinate transformations are. So you have to identify the appropriate cluster coordinates, and those are given by certain holonomies around loops in this filling. Well, as we said, these coordinates were holonomies around loops in the Lagrangian filling. Okay. So indeed, so the explicit calculation calculate explicitly that this is a coordinates related by cluster X transformation. There are 2 types of cluster varieties, cluster X variety and cluster A variety, and this turns out to be the cluster X variety. Okay. So this story is this work of these people, and there's subsequent work of those people as well. Okay, so we found a symplectic home. This is not the first. I should mention that there's prior work. Well, it'd take a long time to give all the credit. The cluster variety is work of Fomin, Zelevinsky, Goncharov, Fock, and even in the symplectic setting, there are examples of cluster transformations by early examples by Paul Seidel and Denis Roux, and there's a lot of subsequent work by Gross, Hacking, Kiel, and Pansevich. So this is maybe another in the story of symplectic realization of cluster theory. Wait, so I forgot to say one thing. This moduli space arises one more place as a Wild-Hitchin moduli space for an irregular singularity. So I just wanted to write down a differential equation. Suppose you have this differential equation. After all, we're in the applied math room. So there's a differential equation. And suppose you want to solve it. Well, you'd like to have the first derivative bring down an x to the 3 halves. So you might want to try to solve it in series by beginning with something whose first derivative is x to the 3 halves times it. And so that would give you x to the 5 halves. This differential equation is singular at infinity. So if you look at what happens as x goes to infinity, or you can take 1 over x as your coordinate and send that to 0, you can see that the growth rate depends on the argument, the phase of x. Because if this is a positive number or a negative number, this is r e to the I theta to the 5 halves, you get cosine 5 half theta, controlling the growth rate of solutions. And so the growth rate will depend on how you approach infinity. And in different directions, this is the Stokes phenomena, you get different growth rates. Uh-oh, 1, 2, 3, 4, 5. Because of the cosine 5 halves. This is a picture controlling the growth rates. And in fact, the Riemann-Hilbert correspondence relating differential equations to local systems and varieties extends, in the curve case, to differential equations with irregular singularities. Okay. So let's talk a little bit about, so what is encoding the change of growth rates? So this is called the Stokes phenomenon. What's controlling the changes of growth rates? They change as you look at different rays out from the center. So it'll be, in general, some braid, but for a differential equation of degree 2, it'll be a 2-strand braid. And all the information is encoded by the fact that these strands cross 5 times. So what I really am excited about coming here to talk about is just the initiation of a program of asking the same questions in 3D. So in 3 dimensions, what would this look like? So we just tried to build an analogy. Instead of points on circle, this is a 2D. In 3D. Well, we have a graph. So a codimension 1 place where the crossings happen. Not necessarily a manifold, but a graph on now a sphere of directions. And so let's say gamma, and that'll be some edge graph of a polytope. For example, something like this. Tetrahedron. So given that, we can now, given this information, what did we do? We constructed some double cover. So we can make an immersed double cover of this and interpret it as the front projection of some Lagrangian inside J1 of S2. And then we'd have a moduli space of objects as well. And we can eyeball it and tell you what it is. The moduli space is a subset of P1 to the number of faces, because we choose a point in P1 for each face, just like we chose a point in P1 for each arc here, PGL2. But adjacent faces have to, because you have crossings at adjacent faces, they must correspond to distinct points. So that's why it's a proper subset. Adjacent faces imply distinct points. All right, so that's some new interesting moduli space. Maybe it's interesting. I'm interested in it.
How you get lambda?
Sorry?
Can you say again? You get lambda?
Yes. How did we get the lambda here? From that information, we built a double cover over the circle with crossings at these points. And we interpreted that as the front projection of a Lagrangian living in the cosphere bundle. And so we do the same thing here. And so it's harder to draw. I have some pictures prepared. But before I show you the picture, I'll say one thing. There's a dual graph, so if I call this graph gamma, the dual graph has vertices at the faces and edges corresponding to edges. So this moduli space, if you count the number of points in the moduli space, field with Q elements. That's the same thing as coloring the dual graph. So you choose a point here. There are Q plus 1 points in P1 in this field. So you have Q plus 1 choices for a point in P1 for each face. But adjacent faces have to be different, meaning for the dual graph. For the dual graph, you get a coloring. So this is equal to the, what is it called? The chromatic polynomial of the dual graph with Q plus 1 colors. All right, so go figure. That's a cute remark, I hope. Let's do an example, and then I'll show you some pictures about how to, what these things look like and how to construct fillings for them. Because if we have exact Lagrangian fillings, maybe we can get charts and understand if there's some sort of 3D analog of cluster theory or Stokes theory. It's kind of a, I don't know what the result will be, but I'd like to begin studying. Sorry, you have a question?
So this time your projection is again on R2 for the tetrahedron.
This tetrahedron lives in S2 cross R, or R3.
And the front projection is onto where?
Onto S2 cross R. Yeah.
Show this on.
So this we put this inside the infinity of S2 cross R, and then it has a front projection S2 cross R, which I think of as R3 minus the origin. Okay, so let's practice and look at this moduli space. If I take the tetrahedron, then there are 4 points.
What's the ambient object?
Is it the configuration space of points, or is it the GAT quotient when you allow coincidence of points? Say M is inside P1 module PGL2.
Yes.
Do you allow diagonals or not?
No. Yes. You take away only pieces of the diagonal. So some points can be the same.
Okay, but so which GAT quotient are you taking? There are many.
Right. Yeah. So you will get some stacky points where the 2 points.
So no stability. You just take a stack quotient.
Right. Okay. So let's look at this one here. So I need 4 points. Each must be distinct from the other, but I'm questioning my PGL2. So 3 distinct points I can set to 0, 1, infinity, and the 4th point is up to me to choose. Okay. In other words, X can be anywhere in the pair of points. Pair of pants. So that's the moduli space. This is the mirror curve of C3. That's probably where we've heard about or will hear more about in this conference. But in fact, there's a reason for that, because this is the Agonagich-Vafa brane in C3. So if you take the Agonagich-Vafa brane, which has a toric picture that looks like this, and you look at it at infinity, it's a 2 torus, and then you project that infinity, interpreting where it lives correctly, you get an immersion over the tetrahedron with precisely this crossing structure. And so, well, the moduli space of objects is maybe equivalent to a moduli space of branes filling what the Agonagich-Vafa brane does at infinity, and that quantum moduli space is known to be this pair of pants. We have the same moduli space, but I have no further connections to that to report. There's also work of David Nadler understanding this brane as a singular thimble for the superpotential XYZ. Okay. Which is not quite what this conference is about. Yes?
So you take the infinity of this brane and you want to fill it by.
And I want to what?
Fill it by.
I'd like to fill it by various things. So there's as you move this around, you get different fillings of the same torus at infinity. I'll say the following. We get an automatic filling for this tetrahedron from the Lagrangian frame. We'd like to fill these other polytopes. What do I mean? We'd like to construct smooth but non-exact. Or it goes there where it's exact but singular. So I'm not proposing that we have a chart of objects. In fact, we have a moduli space which is a pair of pants, and there's no C star that lives inside the pair of pants. So you already see that maybe there's some issue, but I think it's probably an interesting issue to contend with.
Yeah, so in the 2D case, you had basically double cover of the circle with some points, branch with some points.
Yes.
In the 3D case, you have a double cover of the tetrahedron branched over. What is exactly the
Over the edges of the tetrahedron.
the edges of the
Yes.
tetrahedron, not the dual graph? Which
No, it's branched over the edges of the
I
tetrahedron.
see.
I'm sorry.
So I would show you what that looks like, as well as what happens at the vertices. So at the vertices, yeah, it's a hard picture to draw. I can't do it. What else can we do while we wait for pictures? Oh yeah, so I can tell you a little bit about what we do. So we have this tetrahedron that we can do. But now if you have a more general polytope, what do you do to make a filling? Well, what you can do is triangulate. It turns out you don't triangulate the polytope, but rather the dual polytope. Once you triangulate, you turn it into a bunch of tetrahedron, and you fill each of those. But then it's not good. It's not the right filling. So you begin with that, and then you start constructing cobordisms. And if you have fillings, they attach to cobordisms. So a filling will attach to a cobordism to produce the filling of the new object. That's what it looks like over a vertex. Okay, so that's a immersed surface, the front projection of something living upstairs. Over an edge. Oh yeah. Don't try to draw it. This has a name. Arnold gave this
If it's an
singular.
inverse curve, shouldn't the self-intersections form smooth curves instead of stopping somewhere?
They don't. Oh wait, you're saying maybe it's not immersed at this point? Let me move. Sorry, I can't. I think I'm already going over, so I'm just going to show you pictures and then we'll take questions. Near an edge, it looks like that. So there's a picture of the edge. This is a pre-image here. If you look upstairs at the actual curve, not just its front projection, you get an annulus because these are like branch points. And you have a curve, a loop in the actual Lagrangian for each edge. And there's a picture of the annulus that you get over each edge. that's what happens. There's the wavefront projection. That's a double cover over the tetrahedron that I was unable to draw, but we've been talking about it. I should stop, and then if somebody asks, I'll answer the question about the fillings. But let me stop there because my time is up. Sorry. What was the question?
Paul asked.
No, Paul's question I didn't understand well enough or to answer in real time.
Do you have an understanding of how, for the two-dimensional case, you take your front projection and you move it so you get some alternating thing that you have nice charts on? Do you have some sort of cluster move that you can do here?
No, I don't have an understanding of that, and I don't even know if it's on this. Oh, sorry. I do have the cluster move. I don't have coordinates for the charts that fillings give rise to, or if they even give rise to charts. But what you do, in order to construct a filling, I won't explain this, but I'll just show you that it begins with taking your polytope and looking at the dual polytope, and then triangulating the dual polytope. And then with each of those tetrahedra, you then get fillings. And then you need to do a cobordism to sort of untriangulate it. And so the cobordism looks like that. It's just sort of, this turns into that. And then, but there are different ways to have initiated this procedure. You could have triangulated this thing in two different ways. So there are Pachner moves, which are analogs of these 2-2 moves. The 2-2 moves are minute, come from different two-dimensional triangulations of a surface. And so the Pachner moves relate to two different three-dimensional triangulations. And so if you did that here, I would triangulate this same red dual polytope a different way. This is the 3 and the 2-3 Pachner move, if you're familiar with that. And then there's a cobordism that you do, and you can kill something that arises. And you can show that you get, at least at the level of Betti numbers, you get the different fillings that have the same Betti numbers. But I don't expect them to be isotopic to one another, just as they weren't in this case. And sorry, to answer your question, we know that they're not isotopic because they defined different charts. We do the cluster transformations. If they were isotopic Lagrangians, they would have defined isomorphic charts.
More basically, what's the topology of lambda? Can you draw a front of lambda? In the old center front?
I mean, the front just looks like this, or a more complicated version of this picture.
No,
the topology of it is the genus is the number of faces minus 3, turns out. And the filling has you can construct the sheaf corresponding to the filling, and it has, you don't know its cohomology, but you construct its endomorphism chain complex, and that has cohomology equivalent to the cohomology of a handle body for a genus G surface. So it looks good. No, silly. These ones. No, I'm not looking at Oh, you are off. Yeah, so these are smooth but not exact. So not so good for a projected object. This one's exact. Something.